Hey everyone, today we are going to go over some trig integration. Um, and they're just using some different techniques. None of them are, some of them are intuitive, some of them just are not. So I want to show you kind of some differences in how we would go about this. Okay, so example one says evaluate the integral of cosine of x sine of x dx. Um, the first thing I think to try is maybe some algebraic or trig manipulation. Um, there's really nothing that stands out to me, but here, if I rewrite this, we have the integral of cosine of x sine of x cubed dx. So I have a function within a function. Um, so I have a composition here, which screams u substitution. So that is what I'm going to try. I'm going to say u is equal to sine of x. So du over dx, the derivative of sine is cosine of x. And so du over cosine of x equals dx. So we can plug this in, and I get the integral of cosine of x u cubed du over cosine of x. And so the cosine and cosine, they cancel out, and I get the integral of u cubed du. Now we can integrate this, and we get u to the fourth over 4 plus c, and we can plug our u back in, which is sine. So sine of x raised to the fourth, you can put the 4 here, you can put the thing in parentheses and raise it to the fourth over 4 plus c. Okay, so that's pretty straightforward. Interestingly enough, you could allow cosine to be our u, and then we would have had to do a little bit more manipulation, and we'll see that in the next problem. But something I want to note here is cosine is to the first power and sine's to the third power, so both of these are to odd powers. So sine and cosine are two odd powers. Okay. Here, example 2, we have evaluate the integral of sine cubed of x dx. And now if we do the same thing that we just did, we have the integral of sine cubed x dx. If we let u equal sine of x, and we take the derivative with respect to x, and we get cosine of x, we get du over cosine of x equals dx. If we plug that back in, we get the integral of u cubed du over cosine of x. That's not very helpful. So we get this u cubed and this cosine of x. Nothing cancels. I still have an x in here, so I can't keep simplifying. So that did not work. So we need to try a different u. And typically in these cases, when we get sine cubed, we normally get cosine to a power as well. So when we see the problems, we normally see them in pairs like this. So cosine and sine together. And they're the different powers. And so in this case, what we are going to do, and this is going to seem a little strange, is we are going to let u be cosine of x. So note that sine is to the odd power. And so when we have a function to the odd power, we typically choose the other function to be our u. And the reason this is really nifty. So du over dx, our derivative of cosine is negative sine. So du over negative sine of x equals dx. So bear with me. So this is pretty cool. So I get sine of x, sine cubed of x, du over negative sine of x. Well, one of these cancels, and I get the integral. Let me just bring out -1 out here of sine squared x du. However, our u is in terms of cosines of x. And what's really nice is if sine is an odd power, what happens when we take the derivative, we get so sine's the odd power, so we chose cosine. When we take the derivative, our sine's going to cancel, and it's going to turn into an even power. What we can do with those even powers, I'm going to go to that first page. As we said that sine squared plus cosine squared equals 1. And so because we chose the function with the non-odd power, we get our original function is now to an even power. And so sine squared plus cosine squared equals 1. Let me keep that notation the same here. Sine squared. And so I know that sine squared is equal 1 minus cosine squared. And so I can substitute that in. So I get -1, the integral of 1 minus cosine squared x dx. And our u was cosine, du, not dx. We did not change that. Du. And our u is cosine of x. So I can redo this. I'm going to go ahead and multiply that -1 in because it's kind of bugging me out there. So -1 plus cosine squared x du. And then I can say this is -1 plus u squared du. And now we can integrate this. So we get -u plus u cubed over 3 plus c. And so this allows us to rewrite our u's back in. And our u was cosine of x. So I have negative cosine of x plus cosine of x cubed over 3 plus c. Okay, so why in the world does this work? And why did I write this note that the sine is to the odd power? So like I said, these normally come in pairs. So our first problem was cosine and sine. This particular one was just sine. Typically, it would have a cosine with it. If we choose, come over here and write a little note. If we identify the trig function with an odd power, so if we identify the trig function with the odd power, so in this case it was sine, we let u be the opposite trig function. What happens is one of the odd powered functions will cancel out and it will become even, and we can use that identity of sine squared x plus cosine squared x equals 1 to transform our even function into terms of u. Now, these can get way more complicated when you do have sines and cosines in there, where you have to kind of multiply things out. And in this case, we could have done the same thing for this particular problem. So cosine of x, sine cubed x. It was really nice that when I let u be sine, the cosines cancel. I get this nice problem. I could have let u be cosine. And if I had done that, I would have had to use the same identity, but we would have gotten the same answer. It would have been more expanded, but using identities, it collapsed down to the same answer. Okay, so when integrating trigonometric functions that are sines and cosines in pairs, if one of them is odd, we can kind of do this cool little party trick. Now, if none of them are odd, then we have a not so fun problem. And I'm going to show you one example, but you can kind of imagine how they would get a little worse. So let's move on to example 3. And example 3 says evaluate the integral of sine squared x. So let's look at this. Let's try what we were doing before, even though it's not odd. If I let, sorry about that, guys. So we're going to have sine squared x dx. If we let u equal sine of x, du over dx. So a lot of people will say, well, can't we just say the even one is going to be our u? That doesn't always work, and here's why. This is cosine of x. So du over cosine of x equals dx. So the integral of u squared times du over cosine of x. Well, notice I don't have anything to cancel out with. My cosine isn't even squared, so I can't even use that identity. I'm stuck. We can't go any further. So it's not about just identifying which one's even and using that. It's about identifying which one's odd and choosing the other function. And if they're both odd, I would pick the one with the highest power and let that be our u. Okay, so what can we do here? Let's go back up to our identities. Changing it to 1 minus cosine doesn't really help us. However, I do have this half angle formula that says sine squared of x, or a, is 1 minus cosine of 2a divided by 2. So let's do that. So we know that sine squared x is 1/2. And I can never remember if this is plus or minus, so I'm going to go back up here. It's minus. So minus cosine of 2x over 2. So that's our identity. I'm going to rewrite this. So I get the integral of 1/2 minus cosine of 2x divided by 2 dx. Okay. Cosine's not being squared. There's nothing weird going on. We can actually just integrate this. So I get 1/2 x minus the antiderivative of cosine is sine. So minus sine of 2x. And we already had a divided by 2 down here. This 2 right here gives me divided by 4. Plus c. And so we get 1/2 x minus 1/4 sine of 2x plus c. So what's happening down here is we already had that 2 from above. And then when I integrated this, I did a u substitution in my head because this is linear. I can multiply it by 2. So this 2 gives me this. And this 2 was from here. All right. So kind of the moral of the story. If we have sines and cosines that are both even, then we need to use the half angle identities. Okay, and so if you're in my class, I'm also going to include a lesson from before where I do one with a sine squared, cosine squared, and then I do several problems with sines and cosines, but this is just the main lesson that goes with the book, and I'll provide that supplemental material. Okay, so Eli wants to know the difference in the strategies for evaluating cosine cubed times sine squared x dx versus cosine squared x sine squared x dx. Well, in this first one, I'm going to label this one 1 and this one 2. In 1, we have an odd trig function. And that is cosine. So cosine x cubed. I should say an odd power. I keep saying odd and not including power. So let's do that. So let's say odd power trig function, that is cosine cubed. So when solving this, we would let sine of x be u. So u would equal sine of x. what would happen is this would become u, our sine would be u. One of these cosines would go away, and then we could use that Pythagorean identity, which sine squared plus cosine squared equals 1, to substitute it back in, and it becomes a u. So everything quickly becomes a u in this case. In problem 2, we do not have an odd function, odd power function. So in this case, we would use the half angle identities on both sine and cosine, then multiply out and integrate. So two completely different techniques based off if both sine and cosine are odd, or if both sine and cosine are even, and you have one that is odd. All right, guys, I hope you have a wonderful day, and let me know if you have any questions.